next function we're going to cover is exponential function. In general, this function has the form of y equals b, this will be 2 will be our example, b to the power of x. And we already mentioned this, that b we are calling base. And from this moment on, we are assuming that b is either between 0 and 1 or between 1 and infinity. So we are not allowing negative values, we are not allowing 0 and 1, because in those cases we would get just constant functions. We don't need this. And the only values permitted are those between 0 and 1 and those between 1 and infinity. Okay, then of course the upper part of the function here we call exponent. And in this case, the domain of the function are simply real numbers. So any number, any real number we can imagine to put over here. Okay, we're gonna, of course, start like every time with a simple example to explain how the function works. And the example we are going to use is, as I mentioned already, the example when we've got 2 to the power of x. And as usual, we're going to start with a table to understand how this function works. Okay, so we've got -3, -2, -1, 0, 1, 2, 3. Okay, so let's start slow. If x is 0, of course any number taken to the power of 0 is 1. Now if x is 1, then we've got 2, right? If x is 2, we've got 4 and 8. Then we would have for 4, 16, and so forth. Here, x to the power of -1, remember, means 1. The 2 to the power of -1 means 1 over 2. Then we would have 1 over 4 and 1 over 8. And look, even this simple example will allow us to get the proper shape of this function. Okay, so look, this time we don't need negative values of y, because look, if I take a positive number to any power, I will always get any real power. I will always get a positive number. So all the values of this function will be above x-axis, where values of y are positive as well. Okay, and look, what do we see over here? First, when x is 0, y is 1. Now, what happens then? When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. So we clearly see that the values of this function are increasing, and they are increasing faster and faster. Look, by 1, by 3, by 1, by 2, by 4, then the next increase will be by 8, by 16, by 32, by 64, by 128, by 256, 512, 1028, 2056, and so forth. So look, each time when x is increasing by 1 unit, y is increasing by a bigger and bigger and bigger number. Actually, this is an example of exponential growth. So it's growing faster and faster because base, okay, not now. We will get to this a little bit later. I don't want to confuse you too much. Okay, now let's see what happens when we move in the opposite direction. Okay, look, if x is -1, we see that we will have half. Then for -2, but 1/4, we will have 1/4. Then for -3, 1/8. So look, here when we move to the left, we see that actually values of the functions are falling by a smaller and smaller number. But of course, if we go from this perspective, look, here the value of the function increases by 1/8, 1/4, 1/2, 1, 2, 4, 8, 16, and so forth. So look, if I connect all those points, I'm sorry, I'm not a robot, really hard to draw, but I think this will be more or less okay. So this function has the following shape. Here it increases always by a bigger and bigger amount. We can actually see the power of this increases over here when they are taking bigger and bigger values. They're above 1, right? Okay, so this is how we get this function. Now let's try to do a little manipulations with it, just like we did before. Okay, so what if the function that I would have to draw right now would be y to the power 1/2x. Okay, there's one thing we should notice about this function. Look, this function is the same as 2 to the power -1 to the power of x, right? And we remember that we can multiply those, so we get that this is nothing more than the 2 to the power -x, right? This will actually give us a hint on another transformation we have not considered yet. Okay, so let's look at the values. Well, for 0, it's still 1. But now, if x is 1, we've got 1/2. Then we've got 1/4, 1/8. And the in opposite direction, 2, 4, 8. So, what are we getting out of this? If I now connect all those points, I will get a function that looks like this. And what do you really see over here? This is a mirror reflection of our previous function with respect to x-axis. I'm sorry, y-axis. Now, so what transformation we actually used over here? Look, it turns out that if I'm going to impose minus in front of x, what is happening then? Well, positive x's are becoming negative x's, and negative x's are becoming positive x's. So, of course, we need to get a mirror reflection of the previous function with respect to y-axis. Okay, now let's try some different transformations of this function, which are going to be very relevant to the future economic issues we're going to be considering with exponential exponential function. Again, y to the power 2, y equals to 2 to the power of x is still our point of reference. But now let's consider, what if I'm going to impose a coefficient on this function. Okay, so if I'm going to impose coefficient on this function, let's see what happens to the values. Well, first, every value that we've got over here now needs to be multiplied by 3, right? So, instead of 1, I'll have 3, 6, 12, 24. And over here, 3 over 2, 3 over 4, and 3 over 8. Okay, let's see this on the graph. Okay, so this is our original function. Now, if I want to use this transformation, the best point to start with is, of course, a point where x is equal to 0. Because, like, look, we can see, look, what is actually happening to this function is that the slope of this function is getting higher. So the curvature of the function is changing. It's going to be rising 3 times faster. Like, the slope should be 3 times bigger. Right? Because this is what we expect, because we multiply the function by 3. But first thing we will be able to see over here is that instead of 1 as an intercept, we will have 3. But look, now the values of the function, when we move to the right from 3, are growing 3 times faster, right? And when I move from 0 to negative infinity, we see that they are falling. But they are falling 3 times slower. So the function that we're going to get will look like this. Okay, so we see here that the curvature of the function increased, and the function is simply 3 times steeper. Okay, so let's consider a different transformation right now. Let's just say that the transformation we want to try now is, what if I would have y to the power, we have y equals 2 to the power 2x. Well, in this case, we can also transform it. But it's unnecessary. I'm just going to show that it is possible, but of course, look, this is the same as 2 to the power of 2 to the power of x, right? So we could write it as 4 to the power of x. Yeah? So, let's start with a table, as we usually do. And what do we have? When it's 0, it's still, when x is 0, it's still 1. But now, if x is 1, we get 4, right? Because 2 to the power of 1, if x is 1, we've got 2 to the power of 2, it's 4. Or 4 to the power of 1, which is 4. Again, here, 2, we will have 16. Because here we have 2 to the power of 4, or 4 to the power of 2. Here, we would have 64, because we've got 2 to the power of 6, or 4 to the power of 3. And by the same token, we see that here, we will have 1 over 4, 1 over 16, and 1 over 64. So how should I draw this function right now? As you see here, it starts from lower values, but now the function increases faster and faster and faster. And look, the important thing to notice here is that, look, at the beginning you can see that when I impose this 3 here, this function got steeper. But look, this function actually, as x progresses, rises even faster and faster and faster. And at some point, and you can clearly see over here, it overturns the 3 I've imposed on the previous function. Okay, so now we've seen 3 different transformations. What happens if I impose minus in front of x? What if I impose a coefficient on the entire exponential function? And what happens if I impose coefficient on x in the exponent? But we also discussed that this function is working in such a way that it grows faster and faster and faster and faster. But now, what is happening when we move into negative infinity? And look, when we move to negative infinity, we see that those values are getting smaller and smaller and smaller and smaller. But will they reach 0? Well, no, they can't, because look, there is no power. Will they go below 0? It is impossible to take 2 to any real power and obtain a negative value. So we get we see that clearly those values will be getting closer and closer and closer to 0, which again we should take that the x-axis over here has a hidden asymptote inside, right? So this will allow us to do a couple of additional transformations on this particular function. Okay, and look, the next thing I wanted to try with you is to see what will happen if our function will become a little bit different. We will have y equals 2 to the power absolute value of x. Okay, and again, we will see here that we will start with simply 2 to the power of x. Okay, and now let's see step by step what will we get if I impose absolute value over here. Okay, and look, in this case we're going to take an intermediate step. In the table we're going to put absolute value of x, so we have 3, 2, 1, 0, 1, 2, 3. And look, now we put instead of absolute value of x over here. So what numbers are we going to obtain? Like here, nothing changes. Still 1, 2, 4, 8. And over here, if x is 1, we get 2, then 4, then 8. So how will this function look like? Well, here, it does not change. But look, over here, instead of this part, we are obtaining a mirror reflection with respect to y-axis. And this actually leads us to another rule. The rule is simple. If you've got a function y equals f absolute value of x, then what happens is that this part of any function for positive values remains the same, while this gets cancelled completely, and instead we get a mirror reflection of whatever we've got over here with respect to y-axis. Okay, let's make here look, another, let's just say, unusual change. So, what if to this function now I would get added minus? Look, so over here we would have negative absolute value of x. So all those numbers, well, except for 0, would become negative. But what would happen over here is even more interesting. Because now we would have 1 over 8, 1 over 4, 1 over 2, 1 over 2, 1 over 4, 1 over 8. So look how this function would look like. I hope you can guess that this function would look like that. Okay, and okay, let's just try one more thing, because I wanted to show you one other property over here, because we haven't used asymptote, and this is one thing I don't like, so we definitely should. Okay, let's just say that the function we need to draw looks like that. Y equals 2 to the power of x minus 2, absolute value. That's it. Okay, but I just wanted to stress one thing, but we don't need any more complicated example than this. Okay, so we start, of course, with 1. Yeah, I just got used to it. With the function 2 to the power of x. Okay. Now, we will go through a couple of transformations. First one, I have 2x minus 2, and then the next one, I'm going to take absolute value of that. Okay, so first thing we need to do here is to move this function 2 units down, right? It's actually really easy to do, as long as we remember that there is an invisible asymptote over here. So all I have to do is to move this 2 units. The new intercept is going to be a negative 1, and the function looks something like this. Now, the last transformation, we need to impose absolute value. So, look, right away, absolute value changes only negative numbers. So this part stays the same. Now, here we should have mirror reflection. So again, the easiest way to obtain it is by drawing an asymptote and the function we've got looks like this. Okay, now, look, I hope all this is not coming to you very hard, but you should notice that in all of these examples, I was using 2. Why was I using 2? Because it's easy. Look, when you've got a base equal to 2, we can easily make a table, we can make all the calculations very, very easily. But base 2 is not a base that we use very often. The reasons for that, so-called natural base. What is natural base? Natural base is E. Look, we already discussed where E comes from. We know that E is also approximately 2.72, which definitely makes all the examples with it very unpleasant. But it has a lot of nice properties. It assumes we expect it in the context of constant growth, and in the context of calculus, we get extremely simple derivatives and integrals associated with e to the power of x. This is why it is our preferred base. This is the base we want to have. Now, how will this function look like? Look, it will have more or less the same shape as 2 to the power of x, but not exactly, right? Still, if I can draw it, if I want to draw it, I would draw it exactly the same way as 2 to the power of x, because I'm not a robot. Of course, the computer will graph it slightly different for it, in a slightly different way for it. So, what the values are we getting? Look, still, if x is 0, y is 1, because any number taken to the power of 0 is 1. We have just problems with 0, but this is the thing we discussed. Now, what if x is equal to 1? Well, y is equal to e. If x is equal to 2, y is equal to e squared. If x is equal to -1, y is equal to 1 over e. If x is equal to -2, y is equal to 1 over e squared. And of course, we could calculate all these values, but this is not something very useful. But of course, remember, we in economics will be using E as a reference base most often. Okay, so thank you for your attention. In the next video, we're going to tackle logarithms.